Good morning, everyone. Welcome to the NRIS Best Practices and Tools for HPC training event, day 1. My name is Tanya Pushpadas. I am the course coordinator at NRIS. Welcome to the course and thank you for your interest in our course. Before we go further, introduce our colleagues, instructor and helpers, I would like to give you some practical info that you already received on your email. First and foremost, NRIS. Who are we? NRIS stands for Norwegian Research Infrastructure Services, which is a collaboration of Norway's 4 largest universities, universities of Bergen, Oslo, Tromsø, and NTNU in Trondheim, together with Sigma Tour. So we collaboratively operates the national infrastructure services in Norway. So this is part of our training program, and this is the first of the year. We usually give training every semester. So as you can see, the collaborative document I share, the link you got via email, this is where we use, this is which we use to ask questions and collaboratively interact during the training event. As you can see, I'm recording this event. So please feel free to switch off your camera. We will make these recordings publicly available after reviewing and editing as soon as possible after this event. So as I mentioned, the collaborative document contains all the general information about NRIS documentation, workshop page, and this document, also the lesson material that you are going to learn today, which is linked to this collaborative document. And also we collected some your wish list during the registration. So I have summarized all your wish list and tried to give some answer, and please look into it. Then this, as you see, that this is what we are going to use for Q&A. How to do that? Use this pencil icon on top left of the documents and edit it. Here you have some icebreaker question already, bottom of the page. What do you know about computing that you wish you knew earlier? We would like you to edit your answers here. And also bottom of the page, you could ask your questions. There will be helpers who will answer during this event. So further, some practical information. You have been asked about NRIS user account. This course will be mostly demonstrated. So all who applied for the NRIS user account, your access has been granted. You should have received an email. All who already have an account on NRIS clusters and provided your username during registration, you will have access to the training project that we will use during this event today. And I just want to emphasize that this is not mandatory to have an account on NRIS cluster, because this is a generic topic and most of this demonstration should work on any other cluster, provided the specific software modules are available. Yes, actively use the collaborative document. And I would like to introduce you our instructor of today's event, Radovan Bast, and then we will move the introduction towards our expert helpers who volunteered to help during this event, Maikin and Enrico. But first, go to Radovan. Radovan, hi. Can you please introduce yourself?
Very happy to. Hi, everybody. So nice to see so many learners here connecting. Also, hello from people joining from outside Norway. I think we have a few people from Finland and other places, and that's really exciting. My name is Radovan, and I will be really leading you through this lesson. I'm working at the University of Tromsø. In Tromsø, we are today expecting the sun to return, so it's a doubly exciting day. And yeah, really looking forward to this. And also big thanks to a couple of helpers who helped me today. Maybe you can also say a few words. First, maybe Maiken.
Yeah, I'll just be in the background, maybe asking some questions once in a while, but I'm in Oslo and I'll be working on the question and answers in the background.
And then
Yeah,
there is
thanks.
Enrico from Aalto.
Hello, everyone. I'm Enrico from Aalto University, and I will also be in the background, especially if those who are not in the NRIS cluster and want to try those exercises. So get in touch with me.
Thank you so much, Maiken and Enrico, for helping, and highly appreciate your help, Enrico, especially. I'm unaware about any Aalto cluster specification. Your presence is very valued. I just forgot to mention that I work from University of Bergen as a collaboration of NRIS. Since Maiken mentioned she's from Oslo and Radovan is from Tromsø, so we covered most of the cities, 3 cities in Bergen, in Norway now. Yes, is there anything I forgot to mention? Yes, one thing, this code of conduct. So since we are many people are learning together, we follow a code of conduct that's mainly being respectful and use friendly respectful language while you ask question on the collaborative document. That's I just want to mention before we start. Over to you, Radovan. Excited for the event, and I wish
All right.
everyone a good experience.
Thanks so much. I will take the screen. Here we go. And maybe first thing on my list is I want to remind again about the video. So I recommend everybody to turn off your camera and turn off your microphone, because we are recording this and we will put this on YouTube, but we will also edit it. So don't worry if somebody accidentally appears, we will edit you out. But to make it easier for the person editing this, we recommend video and microphone off. However, it's nice for me as an instructor so you can still give me the feeling that you are listening and that there are people here in the classroom, and you can do that by using this collaborative notes. So this document you can edit. There is on top the edit button, and you can write here, and please do so. We edit for you a couple of icebreaker questions. This is all, maybe they are fun, but also this is to test so that to verify that you can all edit this document. And here below is the place where I would like to ask you to ask questions. The more questions, the better the course. So this is the interactivity will come through this. I will be watching this. I have a different screen where I follow this, and I have here Maiken to help me if I miss any question. So please use this document. You find this document, the link to it in your email. You also find it on the Zoom chat. And on top of the document is the link to the lesson material. If you follow this link, you land on this page. And this is the material that we go through today. I know the font is a little bit small. I will zoom in. I will first give you an overview of what to expect. The lesson is on public internet. It's open source. It will stay there. You can also find it later. It will not disappear. What we will do today is a course that it's the first time I teach this. Exciting, but it's really a course that I wanted to have. It's a course that I wish I had when I did computational research. And what we will try to do is I will discuss strategies on how to approach the problem where you have many similar calculations which could be run independently. They don't depend on each other, and how to run them parallel, ideally at the same time, instead of running them one after the other. I will show you different tools on how to approach this. Towards the end, we will also see a tool called Snakemake. This course is not about how to parallelize with the message passing interface or OpenMP. So this is for a different course. So in some sense, what I will do today is simpler, but I think it's really useful. Now, how to participate? I will have here 3 things open. And also the reason why I use more like a portrait screen share instead of landscape is that I encourage some of you who want to type along with me on the other half of your screen, you can then try these things out with me as I type, if you want to and if you can. But I also know some of you maybe don't have access to a cluster or cannot log in, or maybe don't have some software available. So a really good way to participate will be to also watch what I do and ask me lots of questions. So I will demonstrate all the steps. If you want to try it yourself, here is a recipe on how to get the example. But this is what I will do in a moment. So I'll be using this page. I will be using the terminal, which is the dark thing on top. So in a moment, I will log into one of the Norwegian clusters. I will log into the From cluster. But I also wanted to give you an overview of what to expect here. So this is not a beginner's course, but I will still spend 10 minutes on just the basics. What are we trying to do here? What is a scheduler? I will then introduce an example. We will have an example computational problem. We will look at images from on stars, night sky, and we will try to count the number of stars computationally. Just to have an example which is a little bit more fun than Hello World or sleeping for 10 seconds. But this course is not really about this example. It's about how then to process, instead of processing one input file, processing many input files, 50 input files. We will first do that with manually using shell scripting. We will do a loop where we iterate over many similar calculations. Then we will take a 10-minute break. After the break, I will talk about job arrays, which is another way of running many similar calculations. I will talk about the pros and cons. So there are some advantages, but there are also really many limitations. And then I will hopefully spend a lot of time on trying to solve this with a workflow management tool. And the example that I will demonstrate is using Snakemake. But it's just an example. It's more about what I'm trying to do today is that we together think about the problem and gradually, step by step, improve it. And I want to make sure that I can see the questions. And there is already question number 1, and I will try to answer that now in the next section. So I will now go. I don't need the terminal quite yet, but I will need it in, I don't know, 15 minutes. So I will return to this. I will now go into the first episode and talk a little bit about what is a scheduler and what is Slurm and what am I trying to do today here. And if you want, you can navigate there with me. I will be today working on a supercomputer or cluster, 2 different names for the same thing. It's a large collection of computers, and I will sometimes refer to them as nodes. So when I talk about compute node, it's a little computer. They are all interconnected. There are lots of processors. There is a lot of memory, and now there are many people who want to run the calculations. And now enters Slurm. Slurm it's a tool that helps us with scheduling and queuing and monitoring of jobs or calculations. And I like to think of Slurm as the maître d' at the restaurant. So there's the person when you go to a restaurant, it's the person who greets you and asks you, how many people are you? 4 people? Do you have a reservation? No, you don't? Okay, that will be a little bit of a wait. And that's exactly what Slurm does. So we are trying to get onto these resources. We are trying to run calculations, but there needs to be a tool that manages this in a good way and manages the queue, the waiting line. And this tool is available on most supercomputers. Slurm is the most widely used job scheduler in high performance computing. And the visual analogy that I like to imagine, it's like this game here, and maybe you have played this game where blocks are falling from above and you try to fill the rows and pack it in a very efficient way. And I like to think that the scheduler does something similar. So in a simplified picture, these different colored blocks are calculations that I want to do. One dimension is number of cores. Core is like a processor, is like a CPU. It's not exactly the same thing, but for our purposes, we can think of it as the same thing. So let's look at the pink block. It could be a calculation that I want to do. It needs 3 cores, but it will run for 2 time units. It could be 2 hours. And now these blocks are falling from the sky. People are submitting jobs to the scheduler. And what the scheduler tries to do is to pack it nice, tightly, like in this game that I showed on screen above. For the scheduler, calculations are rectangular. Actually, not quite. I will comment on that in a bit. And what the scheduler tries to do is to try to fit the jobs into the available resources. In other words, trying to keep the bottom row always full. The scheduler wants to keep all the core busy all the time. What you want to do as user of the resources, you want to get your job started and finished as soon as possible. So that's our motivation as a user. And then there are different jobs. Some take a long time, not so many cores. And then that's the violet one. The green one doesn't take much time, but takes 5 cores. And if we stay in this nice visual game analogy, we also understand many concepts that happen when you are on a cluster. Imagine that right now the pink job suddenly finishes, and it frees up a 4 times 2 block here. So then what do you think the scheduler will try to do here? Well, it will take the block here from above, and it will so-called backfill. It will try to place it in here. So even concepts like backfilling we can explain with this analogy. A job not only contains here are the things I want to compute, but also there are certain directives. So I need to tell the scheduler that how much time do I want? 5 minutes. How much memory? Sometimes I need to specify the memory. How many tasks or cores or CPUs? In this case, 4. And you also often have to specify what is my project, what is my account, where this should be built to, or the resources that I consume. Here, I will not go into much more details. You can read more if you're interested, because we have different courses that really talk about how does a scheduler work and how do I get started. The very few commands that I will use sbatch, which is the command to submit a script to the queuing system. I will use sq, and that will show me all the jobs that I have and their status. And maybe I will need to cancel a job, and then I can do that with this command if I know the number of the job. I mentioned further up that jobs look like rectangles. In fact, it's maybe better to think of them as little cubes, because there is an additional dimension memory. And they are also not always perfectly rectangular cubical, because if you look inside a job, some jobs at the beginning need very few resources, then later in the calculation they need more, and much later they need less again. So sometimes it can happen that there is all the gray blocks here are resources that I have requested, but that I'm not using. And then there can be different strategies on how to do this better. So in this case, I would maybe try to chop this up into 3 pieces and do this in 3 steps. And I will show you later a tool that does this very nicely. I'm just taking here a few seconds to breathe and read up on the questions. Yeah, exactly. So this is the question 3 here. If you have a job that has a very uneven demand on either the number of processors or the memory, it could make sense to split it into different steps. And then the different steps can demand different things from the scheduler. And with this, it might be that your overall computation finishes sooner, and you will also spend less resources. And if you have to pay for resources, you will then pay less, and everybody else will be happy because they will be able to use these resources. Today, I want to do something like this here. This is really what we want to do today. Sometimes you have a calculation that looks like this. You have lots of small things, which in principle could be independent. And one way to do them is to do it with, I don't know, a loop in Python, or a loop in R, or a loop in the shell in Bash, where we iterate over the different things I want to do, one after the other. And to the scheduler, it can look like one long job that uses only one core. But since these tasks are independent, what we would like to do instead is, instead of doing them one after the other, since they don't depend on each other, how about I would like to do something like this here, where I would like to give the scheduler the possibility to run them at the same time if it has enough resources. They don't have to wait for each other. And I will show you then few strategies on how to do this. So we will start with an example. And in the example, I will first have one building block. And then I will do 50 times a very similar thing. And then I will show you how, instead of having a very long Tetris piece that has the length 50, I want to split it up and ideally maybe get everything in one shot. But thanks so much for the questions here. This is fantastic. Keep them coming. Thanks for the answers. And we are looking at this, and this gives me this interactive feeling that we are here all working together in the classroom. So please do that. I will now go to the next episode in this material, and I will want to introduce you the example that I want to compute, because it's good to have some example that we will work on. And the example that I came up with is, we will count stars. I will zoom in here. I decided to not have a Python example because not everybody here writes Python. I decided not to have an R example because not everybody writes R or your other favorite programming language. The example that I use is super simple image processing. I will explain it briefly, but we don't need to understand it. Imagine that you have these images. This could be like a image of stars from a telescope. It's actually not a real image. It's generated. So I wrote a code that generates random images from random telescope images because I wanted to have many. If I click on it, it looks a little bit like a star sky. If I would zoom in, you would see that they are a little bit pixely. I was also thinking of playing like Star Trek intro music, but that would be a problem for copyright reasons, if we want to put it on YouTube. So just imagine listening to the Star Trek intro sound. And now our goal is to count the number of stars on this telescope image. And now we only have one image. But later, imagine that we will have many images. I will give you 50 images, but we can imagine what if we have 500 or 5,000. And this counting will happen in 2 steps. And now I need to actually go back. So if you want to follow along with me, what I will do now is I will run these 5 lines on the cluster so that I get this example on the compute cluster. I'll make some space here. I will now log into, this is from supercomputer that's one of the NRISC clusters. And those of you who maybe follow on different supercomputers I hope that this will work for you. If it doesn't work, please don't go away. Just then watch what I do. And now I will run these 5 commands. What these 5 commands do is that they download this example and they create a directory called exercise workflow. So I will copy this into the terminal and let it download. And now we download it. Now I can go back to this example counting stars. And I will try to manage here both the browser and the command line. And on top here, the top right thing, I will also try to show the commands that I type. But everything I will do is also in the material. So if anything goes too fast, you get lost. You can also try to retrace it later. So about the counting out for stars, I will do that in 2 steps. I wanted to have an example that does it in 2 steps. The first step will convert the image to grayscale. Actually, it will convert it to black and white. And maybe you think that, well, this is already black and white, but it's not. Some stars are more reddish. Some stars are more bluish. It will basically figure out which ones, where is the light, where is the darkness. And it takes an input image, and all the input images are under star images. Star images, and there are many, 50 of them. So I can take an input image and I can create this black and white grayscale. And this is so fast that I can even do it here without a scheduler. It will take 1 second. I can even do this here interactively for 1 image. Once I will go to 50 images, I will not do that anymore interactively. Then I will use the scheduler. But here I can try that. So now it was reading this image and it generated this temporary image, which is purely black and white. And then in a second step, I'm counting the connected components. I will show you how the connected components look. But in a second step, I can read this temporary image and create the result. And if I want to see what did it actually, what did it write into this file? If I run this without the redirection, it here computed that on this image there happened to be 425 stars. Now, very briefly, how does it work? It's not important for the rest, but maybe you are still interested. I'm using the open source tool ImageMagick for this image processing. And what the first step does, it will distinguish with a threshold, is this something light or is this something dark? And it creates these connected components. And then it will try to count them. The counting, so what we see here is somewhere very much zoomed in on a small part of the image, of the temporary image, and it will count the connected components. So 1, 2, 3, 4, 5, 6, 7. And it's not perfect because here it will count 7, although there are 9 stars, because if stars are behind each other, it might count them as one connected component. But our goals from here on is not to focus on the image processing part or the imperfections. It's not important that it counts too few. I want to now focus on the part that instead of computing one single image, instead of processing just this one, how should what if I want to process 50 or 500? So that's our goal. How to go from one to many. And it's more about the how do I approach this problem and gradually improve it. And what my hope is that at the end of today's session, we will be able to apply this approach and the thinking to your own computational problem, which is maybe not image processing, which may be biology, or it could be a geoscience problem, or it could be really astronomy, it could be chemistry, social sciences, really anything. But maybe you can see your own computational problem in this. Lots of small things that together take a long time, but they could be independent. Just looking here at the questions. Good. Now, next episode. So let's try to compute this now for real on a cluster. And now I will be using the queuing system. So I'm going to next episode from a single calculation to a parallel loop. I will spend there good 20 minutes, 25 minutes. There is an exercise, but I will walk you through the exercise. We will do this exercise together. I will not send you into an exercise room and wait for 20 minutes because I know that not everybody has the possibility to follow on their own right now. And after that, we will take a break. Let me zoom in and let's see what are my objectives. Have a process for introducing variables. We will see that introducing a variable is a useful thing here, so that I can use the same type of calculation for different inputs, different values. Different values. Instead of different images, it could be different parameters, different angles, different latitude, different longitude, or water depth. I will introduce a loop. And first, we will write a simple loop which will run sequentially, one after the other. Later, I will introduce a loop that is a little bit more elaborate, and it will be able to run things in parallel. But there will be many limitations to this, but it will set the stage for later. And here again, if you want to follow along with me, on the second half of your screen, you can then copy these 5 lines into your terminal. Also, if you don't want to download anything and you just want to browse these files, how do they look? You can browse them here. So here's a link to, if you just want to see what these files look like in the browser and don't want to have them on your computer or on a cluster. The job scripts that we will send to the scheduler, they contain lines that start with sbatch, where I ask for how much time. You might need to adapt it if you are not on Fram, and if you are not on Saga, if you are not on the Norwegian clusters, because here I'm using a specific account and a specific reservation, which might not be available in different places. So now let me turn this thing into a Slurm script, and I will start with one calculation, one image. So maybe we recognize these, the 2 lines that are highlighted are the lines that I was running interactively, but now I will run them as part of a job script. This is a job script here. I still want to do these 2 steps. I want to read this telescope image, generate a temporary grayscale, and then from the temporary grayscale, I want to count the connected components. In other words, I want to count the number of stars, and I want to write the result into here. Right now, I'm only looking at the image 000. What is this stuff here? Here I tell Slurm that please use this specific account. So if you're on a different cluster, you have to change these 2 lines. I'm asking for 10 minutes. Well, it will finish in 2 seconds, but and I'm asking here for one task, one core, one CPU core, because this computation only uses one CPU core. And I will now submit this script to the Slurm scheduler. Let me have more space here. Sbatch count.sh. Count.sh That's the script that is up here. And if I submit it, I can then sq-me to show me all my jobs. Here is my job. It has a number. It's running. And if I ask it again, what is the status? It will probably be already finished. And what the job did is it created two files, this file and this file. And I can verify that this file really exists. The cat command will show me the content of a file. In this case, 229 stars. All right. Now I have not just one telescope image, I have 50. It would be, I could be tempted to write now 50 of these job scripts. That would be really tedious and error prone. The other thing I could do, which would be also really tedious, is to use the same job script and then go in and change 000 to 001 and S-batch and 002 and S-batch 50 times. Also really tedious. We don't want to do that. I want to have a little bit clever approach. And what I find personally really useful is to first try to re-express this problem. I will still stay with one calculation only, but I will try to introduce variables. Because I already anticipate that I will try to have it's something variable. The number of the telescope image is my variable. And here is my next script, which you find in the exercise directory, and I called it count with variables. It still only computes one telescope image. The stars is 000. It still does it in 2 steps. So things look a little bit more complicated. But what I did here, and I tried to highlight the change that I did with these yellow highlighted lines. What I did here is to introduce this variable. And then I can use it. So here I define a variable, I call it name. Not sure this is a perfect name for the variable, but I could have called it telescope number, image number. But the neat thing is that I define it, and here I can use it. I'm using the variable here, and I'm using the variable here, and I'm using the variable here. And then I have defined additional variables, input image, which I can use here. And the temporary image I'm using here and here. It looks a bit more complicated, but the advantage now is that if I wanted to change 000 to 001, I only have to do it in one place. I don't have to do it in 2 places. And this will be a good starting point for later. It will make it easier for me to introduce a loop where I iterate over all my telescope images. I'm keeping an eye on the questions. So I could run this now the same way as batch, count with variables. It will do the same thing as before. It would again create 2 files, this one and this one. So I will not even run it, but if you want, you can try it out. So really not much has changed, but the advantage is that I only have to now modify one line. I still don't want to write 50 job scripts. So now we take it one step further and add iteration. And the next script, and that's the one that I will really test out, is the count loop script. And here is the script. And what has changed is highlighted in yellow. I'm still using the same variables. But now I have a for loop here. For input image, this is a way to ask bash, please locate all the files that end with PNG in the directory called star images and iterate over them. So you have maybe seen this before, maybe you haven't seen this before. This is not a course about shell scripting, so this might be very new, but let's try to look at it from a lot of distance. From a lot of distance, all you need to remember here is that I have a way to iterate over all files with a certain pattern in a certain folder. And this will define a variable called input image. And from the input image, what I do here is I extract the name, for instance, star minus 000 or star minus 001. And then I use it the same way as I did it above in the other script. So this is unchanged, and all the rest is unchanged. I added some lines here where I want to get some information on when does the calculation start. We will see how that is useful in a moment. But really the only thing that changed is that the input image, now I iterate over it and I locate all the images here. In my case 50, but could be 2000. And what we will see is that I will now run it. Let me submit the script. How many processes do we ask for? We ask for one. That sounds good. But what we will see is that it processes 50 images one after the other. First the 000 and then the 001 up to 049. As batch, what was the name of the script? It was called count loop. So if you have the possibility, you can submit it as well on your side. I got the job number. This is my job number. SQ-me. Show me my jobs. Here it's running. And it's still running. And it produces, in my case, an output file. This is the output from the scheduler. And I can even track its progress. So tail minus F, I can live see how the file is growing. And what we see printed here is this echo and this echo. And you can really see that it's processing one image after the other in a random order. So it doesn't do them in the alphanumerical order, but it processes them one after the other. Each of these steps takes a second or two. I see lots of questions coming in. They get answered. The ones that are really, I think, for general understanding of what I'm showing, I will also try to discuss in voice. One after the other. In my case, that's fine. Every processing takes 2 seconds. Who cares? But in real life, maybe your computation would take 1 hour for each. And then you don't want to do it one after the other. So this is maybe another problem for me right now to wait here 2 minutes. And now it finished. So it took a little bit, it took close to 2 minutes. Process all the images. But in real life, it could be a problem for me to wait a couple of days for all of the computations to go through. Yeah, somebody also asked, I will try to answer it a little bit in a general way on how to modify this for other clusters. I'm now presenting from a cluster called From, where we have this reservation and where we have this training account. If you are somewhere else, you probably need to remove this line. You probably don't have that reservation, and you need to change this account to your own. Don't be worried about using your own, because the examples that I will show, they really finish in seconds. It will not really eat into your compute quota in any significant way. On some clusters, you need to define the memory. So this is at the moment inactive. So if you follow on a Saga cluster, which is another cluster in Norway, you might need a line like this to define the memory. So the big picture here was we ran one calculation after the other. We verified this. I was tracking the output of the file. And now I could be tempted that, well, yeah, it was one after the other because I asked for one task. What if I ask for 20 tasks, 20 cores? Well, it will still only use one of the 20. 19 of them will be waiting and doing nothing. It will still run only one after the other. So a common misunderstanding, and I understand where it comes from, because I thought the same, I had the same expectation, is that if you ask the scheduler to give you more cores, I somehow expected that, well, it will also parallelize what I try to do here. But in this case, it doesn't. This only tells, it's like, going to the restaurant and saying that I need a table for, instead of one person, I need a table for 20. But you still show up only with one person at a time. And after I finished eating, the next person takes my seat. So this only asks for the resources that I want to have. The scheduler often doesn't have a way to see what I'm really trying to do and somehow parallelize it for me. So we will have to parallelize it. And I will now show you one way of doing this so that we can compute them in parallel. It's powerful. I think it has certain limitations. So take it with a grain of salt. I just wanted you to see that this is possible. At the end of the course, I will show you a much better way. Here, I will take our script from before, count loop, and I will make a few modifications, and I will call it count loop parallel. And I want to now first walk you through these modifications, and then we will test it out. Well, one modification I will do here is I will ask for 20 cores. We know that on its own, this thing will not do it. So I need to do a little bit more. And things are getting a little bit more complicated. But what I changed, again, I try to highlight. So let me explain. First change I did is that the two steps, I have two separate loops for the two separate steps. So this is step number one, and I iterate over all images. And this is step number two. And then I iterate over all the images. And I will explain why I did that, why I don't do this in one loop, why now I need two loops. But I need to explain more here. The other change I did is that I added this ampersand. And this will tell shell that, well, don't wait until this finishes. Send it to the background, do your thing, and then return to me once you are done. But I can continue. So this ampersand will mean that the script will send this off to the background. It will start computing, but the shell script will continue, and it will continue to the next iteration. And it can continue to the next image. And it sends the next image to the background, and the third image, and the fourth image, fifth image. And then I also introduced this. So then I need to explain what is the wait. The wait statement will wait until all the background processes are finished and returned. And I need to do this to make sure that I don't start more processes than I have asked for. So this contraption here, it looks a little bit complicated, but this is here so that I start maximum 20 background processes because I only ask for 20 cores. And then I wait until they are finished. And then I continue with the next batch of 20, and then the next batch of 20 until I processed everything. So question 9 is the exercise you are basically doing the parallelization in Bash. Yes, so here I parallelize basically in Bash. And although I show that in Bash shell scripting, you could do similar things inside a Python script or inside an R script. So I see many Python codes that this was the sequential example that try to do this. You could do something similar also with the help of Python, with the help of R. Let me try this, but I want to discuss then the limitations of this, and then I will send us all into a break. So on the cluster, I have this. This is the one. Count loop parallel. SBatch count loop parallel. This is my job number. And now if I follow this calculation, I follow the output of Slurm. What, it already finished. Interesting. Good. I guess that's what we wanted. So instead, let me browse the output. This is the output from the count loop parallel. This vi command is, maybe I shouldn't do vi. Let me show the content of it with cat. And it's what we can see that now is different because now it starts several of these at the same time. In fact, let me get more space here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It starts 20 at the same time. And they all take a second or two. And then it starts the next batch of 20. And then here it's less than 20 because we already ran out of things to do. This is here the first loop finished. Here the second loop is starting. Again, batch of 20, batch of 20. And then we ran out of things to do. So this is really nice. They are now running parallel. I was really using 20 cores. But before we celebrate too much, let me make sure that I didn't forget any important info. Yeah, so I can imagine that this part here is really weird to look at. Here's an explanation of what it does, but it makes sure that we, oh yeah, so it makes sure that we don't start more background processes than we have cores, but I didn't explain one thing. I didn't explain why I split it into 2 loops. And the reason for this is that if I didn't split it into 2 loops, it could happen that it starts processing the second step. It could start doing this before even it finished this on an image. So splitting into 2 loops made sure that I first create temporary black and white image for all the telescope images before I move to step 2. If you, for your own experimentation, you could try to do this with 1 loop only. And depending on the number of tasks, you can then get interesting effects if you are not careful about this. So now so we did this. There is also, yeah, I didn't do all of it. I didn't answer this question. What would happen if we increase n tasks? That's important. So in my count loop parallel, Here, I asked for 20 cores. How far can I go? Well, I had 50 things, 50 images to process, so I could ask for 50. It would finish even sooner, because then it would do all the 50 first step, all the 50 second step. But what if I ask for 200 cores? Then I would have more cores available than I have things to do. So it was important for me to point out, and you can then also find it in a solution, is that this thing shouldn't be bigger than the number of steps I need to run. In my case here, it doesn't make sense to go above 50. And now we have 4 minutes, and then I will take a break. I want to mention a few alternatives. So this was one possible way, but it was a little bit clunky. There are alternatives also in shell. One nice alternative is the combination of find and xargs. With find, you can locate all the files that match a certain pattern, and you can pipe it. And I'm sorry if all of this is really unfamiliar jargon, but you can pipe it into a command called xargs, and you can tell xargs to do something with these files. And xargs has an option to run in parallel. So you could express it. It would be more compact. I didn't want to do that because it would be one more thing to learn. So this is just to mention that this is possible. Yet another way, instead of using find and xargs, you can use also find and GNU parallel, which is another nice way of doing basically what I did. Locate files that match something and then do something with them using all available cores. But let us discuss the limitations. One big problem with this is that sometimes your calculation can fail, or they can time out. And what if 10% of my calculation fails? Then, and in fact, if you want to try it out, you can. So there is another script. If you want, you can experiment with this. If you change the line that counts the connected components with this line, I wrote a script that will randomly fail on you 10% of the time. And then you can run this, but then you will notice that, okay, 10% of my jobs failed. And now what? So how do you rerun the 10% of the jobs that failed? Now you need to go into the script and maybe comment out some steps, or you need to add more if the file exists, then run it, or if it exists, then don't. If the output exists, don't do this unless except. So it's possible, but it can get complicated. So my example doesn't know about failures, and if I have failing scripts, it will be complicated. Another limitation. Well, what if I realize that now I made a mistake in the second step? When I count the connected components, there is a better way of doing it. I want to rerun only the second step, not the first step. So now I need to go into my script and I need to comment out lines. It can get messy. I can lose the overview. This counter and wait mechanism is not so easy to read and understand. I didn't come up with it. I also asked the internet. So it's possible to deal with failures and not rerunning finished jobs with shell scripting or Python scripting or R scripting. I mean, everything is possible in any language, but it can lead to a solution that can be really hard to maintain and understand. And I will show you a much nicer way to do that. There is a joke that everybody during their PhD accidentally invents a new workflow management. And workflow management is exactly this. Like you have a set of things to do, but you need to also, some of them can fail, some of them you need to rerun. That's workflow management. And instead of inventing our own workflow management written in shell, I will show you later how to do that in Snakemake. But let's do that after the break. Let's take a 10-minute break, and I will, in the meantime, catch up a little bit with questions. And we will be back 10 minutes after the hour and then do job arrays and Snakemake. See you then.
Yeah, thanks, Radovan.
Yeah, welcome back to second part. 50 minutes left. For those of you who joined later, reminder, we recommend to keep your camera and microphone off. It makes it easier for us to edit the video before we can post it on YouTube. But the way to interact with us is this collaborative notes. And I really appreciate the many questions there. Before moving on, I want to connect. Yeah, I need to mention two things before moving on. First thing I want to mention is that if you are using the Alto Triton HPC cluster, then Enrico has prepared a folder for you which you can copy, which is adapted so that it runs on the Alto cluster. So thanks so much for that. Then you don't need to modify it yourself. And then I also wanted to say thanks for many questions and I wanted to connect to question 10. Very good point there. So one thing I didn't mention, which question 10 points out, is I have to be actually careful with my parallel loop. One limitation, and I need to add it to the material, is I'm asking for 20 cores, and I said you could ask for 50 cores, but 50 tasks, but we have to be careful that we stay within one compute node. I should actually here specify not just the number of tasks, I should also specify that I want to have one node, one compute node. This will probably not work. And by this, I mean the trick of using background processes and wait will probably not work across multiple nodes. If you need to go across multiple nodes, you are better off by using srun. So that's something I need to modify in the material. So that's one really big limitation. But anyway, these days compute nodes have often, I don't know, 128 cores. So one can pack a lot into one compute node. Still, I find this limiting. I find it hard to read. I'm not able to just write this without looking it up. And it can be tedious if some of the steps fail. It can also be tedious if I only want to run, I find an improvement in this script. I don't need to run the first part again. So then you need to go into the script and maybe you have done things like this, going in and commenting things out. But it can be then really hard to keep track of this. So everything is possible, but it can lead to a very elaborate, hard to read, hard to understand solutions. I want to now show you two alternatives. One alternative is job arrays, which also has some limitations, which I will point out, and then we will spend half an hour on Snakemake and workflows. The job array. So many people, when they hear, okay, I want to do many similar things in parallel, they think job array. A job array is a way in Slurm to have like a template. It looks very similar to the single job, if you remember that. So this was the single calculation where I only processed one single image. And if I wanted to turn this one into a job array and compute 50 images, I don't have to change too many things. The changes that I have to do is this one. I want to have an array of jobs, and they will have a number 0 to 49, 50 of them. These two lines I defined because now I don't want to see 50 outputs from Slurm, so I want to write them into a new directory. So this is not strictly necessary, but just to keep my directory more organized. This is the essential line. And then instead of saying name equals stars minus 000, I have to translate I have to translate this number. I have to map it to what I want to have. So each of these jobs will have a different so-called Slurm array task ID. And what I'm doing here is I'm constructing a series of calculations from this ID. So this is like a mapping translation. Everything else is unchanged. And I will submit this. And how is it called? How did I call it? But I will discuss what the problems are with this. I call it job array, count job array. I was just thinking for a second whether this is even a good idea.
Can I just ask another one? I thought the name refers to the input files, PNG files that you already have. But the input files, do they have the number, Slurm array task ID number? Wasn't it 1, 2, 3, 4, 5, and so on?
So the files will be called, let's see the correspondence. The files will be called.
The files are called, or they're
they are
those,
called.
Yeah,
they are called
input.
star images / something. So that's the name of the input image. So what I want to have here instead of name, I want to have, for instance, this one.
Yeah, so the Slurm array task ID will indeed be 1, 2, 3, etc. Or 0, 0, 1, 0, 0, 2, 0, 0, 3. Good.
Well, the Slurm array task ID will be 0, 1, 2, up to 49. So here I'm actually translating what I get from Slurm to what I want to have.
Yeah.
Which here is, I don't know what I should call it easy. It's relatively easy, but or it's possible. I don't know. Also, this is not something I came up with. I had to look it up. But it's relatively easy because I have only one parameter. But we will see that one limitation of these job arrays is that what if you have 2 parameters, 3 parameters? Sometimes you have nested loops and you have various parameters in and now you need to somehow translate this one number into one or multiple parameters, which can get really hard to understand.
Yeah, but that's okay.
One big limitation of job arrays. It's not even the biggest limitation. I think I will just submit this. Maybe we'll see the other limitation. I want to submit the job array. And yeah, maybe I can see that already. Job array doesn't mean that all of them will start at the same time. And in my case, maybe you can see that. So this is my job array. This is the 6th image. This is the 7th image, the 10th image, the 11th image. It's actually running them one after the other. Well, it runs 2 at the same time. In my case, that's because I have 2 nodes available in my reservation. But I think we can already see the limitation. It will, and here I need to explain a little bit for people who are not on the from cluster. The from cluster where I'm now doing this exercise requires me every job to use at least one entire node. On the from cluster, I cannot get just a portion of a node. I cannot get just one CPU. If I want to run only on one CPU on this particular cluster, I will get an entire compute node. If I would try the same thing on the Betsy cluster, I would have at minimum, I need 4 compute nodes. And the limitation of a job array is that it's not a way around that. So if my jobs are required to have at least 1 compute node, also each job of the job array will be required to have at least 1 compute node. I'm actually wasting resources. Here it doesn't matter because it finishes after 1 second, but if this was a real thing that takes hours, I would be wasting resources. I would also not finish anytime sooner. Now it computes the last one. and now it finished. Each of these individual jobs occupies the entire node. So on the From cluster and on the Betsy cluster, for my problem, this would not be a good solution. Because the things that I ask for here will be valid for each of the 50 jobs. And what I don't see here, but it's a little bit implicit, is that this particular cluster, I cannot have just a fraction of a node. If you try the same thing on the Saga cluster, there you can have a fraction of a node. Different jobs can share a compute node. There, job array would be a okay solution. So let me point out the limitations. So for simple cases where I have a single parameter, and again, if the job is not likely to fail, it can be a good solution. If some of my jobs failed, I'm back to the same problem. What do I do now? Because if I submit the job array, it will rerun all of them again. If I have multiple parameters, it can be really cumbersome to map this one number, because from Slurm I only get this one single number, to map it to my 2 or 3 different parameters. Everything can be done, but I just find it too complicated if it's more than one. What if I get now new telescope images? Then I need to go in and adjust this number, and that's error prone. Maybe I forget to do that. And I talked about the cluster limitation, that for good reasons, some cluster want you to have minimum 1 node, 4 nodes, and this is not a way around it. It only makes sense if you can use a fraction of a compute node. And also here, if you want to see how annoying it is, if some of the jobs fail, you can change this line to use the script which will fail 10% of the cases. And then, well, I don't know what to do then. So let's do this better. Let's now we comes the finale for the next 40 minutes, which is let's approach it in a completely different way. Question 15. I'm running this on the compute cluster. This is not on my computer. It's my local terminal, but in the local terminal I have connected to. So this is not my computer. This is a supercomputer which is actually in Tromsø, but it's a Norwegian national supercomputer, one of those. Now we will approach it very differently. We will need to think about the problem very differently, but I will walk you through it. So most of us will be new to thinking like a workflow, but don't worry. I will walk you through it. My goal is that we understand the concept. So instead of thinking step-by-step commands, we will think in terms of dependencies. What do I want? And the thing that I want, what does it depend on? And you will see the name rules. So when I use the name rules, I think of like steps, dependencies. So this is what Snakemake calls it, rules. We will translate the problem that we have into Snakemake, and we will see how Snakemake can do lots of the things for us that were hard previously. Our goal is not to become experts in Snakemake or to remember all the details. It's more to understand the approach. And at the end of this episode, I will also point out alternatives. Snakemake is not the only tool that can do this. There are many so-called workflow management tools, and I will link you to some other ones if you prefer them. And the big picture. So let's start a little bit with the big picture, and a central file is called a snake file, which defines these dependencies. And you will find the snake file in your exercise directory. But let me explain it. What do I see here? So the snake file contains so-called rules. There are 3 rules. One is called rule all, one is called rule count, and one is called rule grayscale. And previously we had 2 steps. The first step was to run the script. The second step was to run a different script. So the 2 different steps, they translated to 2 different rules. Each rule I define what are the inputs. What does it depend on? It depends on not only on the script, but it also depends on input files. What is the output of the rule? The output are the result files. So the second, let's start with the first step. So the first step was we were reading input images, and using this script, we were producing temporary black and white temporary images. How did we do that? This line defines how we want to do this. In the second step, we were then using the other script, we were reading these temporary images generated by the previous rule, and we produced result file which contained the number of stars. How did we do that? So here I've described what are the steps to take from the input files to the output. And now I use this wildcard. I don't have to refer explicitly to 0000001. I'm using a wildcard. And the wildcard I obtained with this command, which will I ask it to find all the files that match this pattern, star images / stars minus, and then I defined this as a wildcard. I told it that this is something that can vary. Everything else will not vary. And then I used the wildcard throughout my definition. There is a third rule which is called all, and that is the rule that will be run by default. And here I describe what are the things that I want to have at the end. At the end, I want to have these result files, all of them. How do I want them? Then Snakemake will see, well, you want these files. How do you create them? You create them by this rule. But in order to run this rule, I also need the temporary images. So I need to first run this rule here. It understands really well of what depends on what. It understands also really well of what is independent of each other, and it will be able to parallelize the things that are independent if I have resources available. So now I don't find it easy to write this, but at least maybe this is a good starting point for your own computation. But once we have a recipe like this, we will see that many things become really nice and really easy. I just want to make sure that I didn't forget any important explanation. We have 3 rules. Rules depend on input, they produce output. And the shell part, here we tell Snakemake how to produce the output from the inputs. And again, I'm using these wildcards. So input script will refer to input script. Input image is this one, input image. And output is defined here. This part here, defines what we want to have at the end. So instead of, I don't tell Snakemake in which order to do things. I tell Snakemake what depends on what, and it will figure out the right order. I will demonstrate this in a moment. And before demonstrating it, good question number 15, is there any key difference between Snakemake and Nextflow? I will mention Nextflow also at the end of the course. Nextflow is a different tool, but with the same philosophy. It's also a workflow management tool. It's a tool that I don't know well. So when I try to solve it, I go for Snakemake just because I know it a little bit better. But everything that I can do in Snakemake, I can also do in Nextflow. Also there you will express dependencies between steps. And also Nextflow lets you manage the workflow. It's a good alternative. And there are 120 other tools, but at least in the high performance computing, I see Snakemake and Nextflow most often. The job script looks suddenly a lot simpler. I will now ask for 20 cores. And now it doesn't matter actually anymore whether this is on one node or multiple nodes. I don't have to be careful about it anymore. I'm loading here the Snakemake module. So it's a tool. This line here will make it available on, this looks a little bit different on other clusters. If you have a different version of Snakemake, not a big problem. I think it's good if it's something that starts with 8. This is the interesting line. Snakemake will find the snake file. This is snake file here. It will find this file, read it, and process it, understand it. I also tell it to use cores. How many? This many. This variable changes if I change this number. So then it's better than writing here minus cores 20, because what if you later you change it to 40 and you forget it to change it here. So I like to use this variable. This variable will be, it depends on this number. And then there is this option, keep going. Keep going means that we already have a feeling what it might be. If something fails, I tell it to just don't give up. Continue with the rest of the calculations. So I will hopefully return to this. Yeah, this command will then find the file. No, sorry, this is now, it will find the snake file and do all the steps. And then there is a question about logging. I didn't comment on that. So I also, because I want to have things nicely organized, I have this folder called results, but I also have a folder called temporary. And later we will see what this means. This is for a little bit later. But I also have a folder with logs. And there you can then write, you can log output or errors from the different steps. So if some of them fails, then you can go into the logs and see why did this fail.
Can I ask if it captures also standard out from the analysis script that you're running?
Just thinking about it. I'm unsure. I think we can define it, and I'm not sure I tested it. So we can control whether it, where you can, I will maybe answer it in a general way. You can control where standard output and standard error will go to. Let's try to verify this in a moment. So now what I will do is I will submit the script and we see what it does. Actually, I will go through this exercise, but we will go through it now together step by step. And step number 1, it tells me, well, submit it and see what happens. And before doing that, I will now, it's not strictly necessary, but just to keep things nicely organized, I will remove results and I will remove temporary. And I will also remove all the Slurm outputs from my previous calculations. I don't need this one either. This is just for, it will make it easier for me to present. If you type along, you don't need to remove these files. It will still work. So this is where my scripts are. I'm now running this one. This is the snake file that I demonstrated here. And here are all my input images. And now let's submit this one. It runs on one node. It will finish very soon. Still running. Gives me a possibility to read questions. And there it's done. It actually all worked. So there are under results are all my result files. If I want to know how many stars are in the image called 038 or 37, it's these many. All the temporary files are under temporary. Here are my temporary images. And here are the logs. Let's look at those. So they are all empty now. So what I'm here, 0. So I'm guessing they will now contain, the way I set it up, it will only be the standard error going in there. Not super sure about it, but I think it's not very important for the rest that I want to discuss. We need to look at the Slurm output. No, I don't want to use cut. I wanted to use cut so that the Slurm output is now longer. I will now scroll all the way up to the beginning of the Slurm output. And let's try to understand it. Oh, this is not good. I will use my editor to browse it. So at the beginning, this is output from Snakemake. It's building a directed acyclic graph. It tries to figure out what depends on what. It's a graph of dependencies. From this graph, it can infer what it can run in parallel and what not. It sees that I gave it 20 cores. And now it tries to find out what are the things that another one wants me to do. There are 101 jobs. What does that mean? It sees that there are 50 computations to be done in the count rule, which is the second rule. There are 50 computations to be done in the grayscale rule, which is the first step. There is one called all, which is the rule to tie it all together. So it has in total 101 things to do. It will introduce them, it will spread them over 20 cores. It knows perfectly well what it can run in parallel and what not. I don't have to be now very careful about it because it will respect the dependencies. And then it runs through all of these things. Here I'm scrolling, and it will just do the right thing. I think the really interesting part will be, how did it know which steps it can start in parallel from the dependencies? Also here, there is a solution. So if you want to later read up on what I'm telling here, you can. I think the really interesting part will be if I submit the script again. That will be really interesting. What was it called? Count Snakemake. If I submit it again, it will finish in 3 seconds. It didn't do anything. what was the number? 633 at the end. If I look at the output from the 633 job, so all of this is from our cluster. The only output that comes from Snakemake are these two lines. Building the graph of jobs, and then it realized, well, there's nothing to be done because all the files that I wanted to have, they are present. And they are not only present, they are also up to date. So it will not redo things that are already there. That's beautiful. This will be also nice once we look at failures. The jobs that didn't fail, it will not run them again. I don't have to be careful about this. How does it know it? Because it looks at two things. It looks at timestamps. It can see that the files in the files under results are all there. All the files that I wanted are there. It will also look at the timestamp. And it can see that the files are newer. They are more recent than my Snake file or the scripts that produce them. So no need to recreate them. It also, it's even more clever than that. It also looks at checksums of files. And I will demonstrate that in a moment. I want to connect now to a question. I think somebody asked, is there any limit on how many rules? I'm not aware of any limit. So you can have 5 rules, 27 rules, no problem. Very typically, if your pipeline, I think most pipeline contain 1 step, but if your pipeline contains 2 or more steps, it will translate to 2 or more rules. There is really no limitation that I'm aware of. Yeah. So it will not repeat the steps that are done. If you really, really, really want to rerun it, you could do it. So I could tell Snakemake, delete all output, and then it will rerun it. Or if I remove the result folder, or if I remove a couple of files, it will rerun only those. And I can, so let's try question 4, remove a few files. Well, let me remove results, but only a couple of them, 007, James Bond, and another one, maybe the 33. I removed them willingly or accidentally. If I now rerun the script, it will produce only these 2. And it right now is maybe a little bit excessive that I give it 20 cores because it doesn't really need 20 cores to reproduce these 2 files, but okay, we will just look away for a moment. So if I run this again, I expect it to not run the whole 50 images. I expect it to only reproduce these 2. And it already finished. Here is the output from Slurm. And the interesting part is this, 20 cores, a little bit too much, but it figured out that it only needs to run this step, the counting step, on 2 of the images. And notice that it didn't even have to do the other step, the grayscale. So it figured out, well, the results are missing, but the temporary files are still there. I only need to run the second step and only on 2 files. These are still available. It only had to recreate 007 and 033. If I would remove both the temporary and the result, it would run both steps on the file. So it's really clever about that. Question 19. Why is this called the rule all? So this rule here. And that connects to, that was in the Snake file. this is the name, this is the default name for, so this is the name of a default rule. So if I type Snakemake, it will find the snake file and it will look for this rule that is called all, and it will run it. I'm actually not sure whether this is really true. It might also just run the first one. And maybe I just called it all. But that connects me to, I think I don't have it in the exercise, but one thing you can also do with Snakemake, and I will now do it only, I will do it here interactively, not through a script, because it is so fast. But I have to be careful. I have to load the module. What I want to show you now interactively, just as a demo, is you can do Snakemake only on one core, and you can only ask it, instead of running everything, I can ask it to please produce me only one of the files. I only want this one. And it actually told me, well, there's nothing to be done because it already exists. But if I remove it and ask it again, it will produce it. Why do I show this? This can be useful for testing, because when you test your setup and you have 2000 data files to go through, for testing and debugging, this can be really nice. You can ask it to only produce one of the so-called targets instead of all of them. And then once you know that this is working, then I can leave this out, and it will then run the first rule, which in my case ran through all the images. Here in also question 21 is really good. If can one of the rules include already parallelized code? Yes. Here, to keep it simple, all of my steps are, we can imagine them as being using only one core. But some of the steps can itself be parallelized and use multiple cores. And in a moment, I will give you hints on how you can do that. Question 20, if you only remove the temporary, does it do anything? Or is it fine with the corresponding results? You can try it out. If I remove temporary and run Snakemake, it will not do anything, because it knows that, well, results are there. No need to recreate them. And if I don't need to recreate them, I also don't need the temporary files. I want to show you a few more interesting things with Snakemake, and that is, we did 4. What if I now realize, I made a mistake in the script? And this is the script for the second step. And now, if I make a modification here, we will see that it will not run everything again. It will only run the second step. So if I modify the script, and it is not enough to just change the timestamp. So Snakemake is clever. It doesn't look only at the timestamp. It also looks at, has anything really changed? It looks at the checksum. So here some important change, important bug fix. Let's imagine we do bug fixing. If I now run Snakemake, what we will see is that it noticed there was a change in the script connected components. Connected components is an input to this rule. This rule depends on it. Since the dependency changed, it will have to rerun the outputs of this rule. It will reproduce all of the results for me. Now let's verify whether this is really true. So this is the output from my latest job. And here I can already see that this is exactly what happened. It reran 50 images, but it didn't have to produce the temporary files because this was only a change in the second step. I will do 2 more changes, 9 minutes left. We will make it. One thing that is also super practical is that now in my star images, I got now new results from the telescope. Instead of having just 50, and I will now be lazy, I will copy the last one and I will give it new names and nobody else will know. But these are now new images from the telescope. 100, 101, 102, 103. 4 new images from the telescope. It could be 40 new images. The beautiful thing is that I don't have to touch anything else. I don't have to change my JavaScript. I don't have to change my snake file because the snake file will automatically collect all the files that are here. But at the same time, it will not recreate the results that are already there. So what is really, really nice is that if I now run it, it will pick up only the 4 new files and produce results for them. Four images. See? And here they are. Here's the one, and here's the other. So that can lead to a really nice setup because you can have a setup where you have a folder where new stuff comes in, and then from time to time you run Snakemake and it will just run the new stuff. And I wanted to show you one more thing, and that is in the snake file, I now want to introduce a possible failure. Here I have the script that can fail 10% of the time, can fail. And at the same time, I will make another modification, which is interesting. I will change this line to temp. Temp is a function that Snakemake has. So this is new, the temp parenthesis. With this, I will tell Snakemake that these files are temporary. If everything works out, you can delete them. I don't need them later. Please only keep them if my calculation failed. Okay, and now I will remove temporary and results. Another way of doing that would be Snakemake delete all output. I just want to show you now how does Snakemake deal with possible failures. Let's submit. I have 54 computations to do. I expect roughly 5 to fail. It's a little bit random, so hopefully some of them will fail. It already completed. And now if I look into temporary, there are only 5 of them are left. Why are there not 54? Because I specified that these are temporary things. If the calculation succeeds, get rid of them. The 5 that are left here are the calculations that failed. And if I look into results, I expect 001 to be missing and 020 to be missing. Yeah, because they failed. So there is no 1, and then there is also no 20. So what to do now? Well, I can just submit again. And if I submit this job again, it will rerun only the 5 jobs that failed because everything else already exists. And I can do that. I can repeat it a couple of times until I have all the results. And I don't waste any resources. There is a bit more elegant way of doing this. And I can see that I only have 4 minutes left. So I want to mention a few things that Snakemake can do. You can also tell it to, if something fails, try to restart it a few times, 3 times, and give up then. The keep going option was to make sure that, well, don't give up on the first failure. Try to complete as many computations as you can. I showed you temp, but there is also protected. Protected is the opposite. With protected, you can tell Snakemake to write protect important result files so that you cannot accidentally delete them or overwrite them. It's possible to use a locally mounted file system. So sometimes network file system can be slow, and I'll link you to documentation. I didn't want to complicate too many things. It's also possible, sometimes you want different rules. Sometimes different rules need different software environments. You can tell Snakemake to use different, for instance, Conda environments for different rules. So that is something that is possible. And here I link to more documentation on, you can do really amazing things. So if this sounds interesting, have a look at the Snakemake tutorial, which takes you step by step. Have a look at the Snakemake documentation. But really, this course here was not even so much about Snakemake. It was more about trying to solve a problem with a workflow. Somebody earlier asked, can a rule use 4 cores or 8 cores instead of just 1? Yes, you can. So what I did was, I did the simpler thing, which was I had a Slurm script which started Snakemake. This is simpler. This is very common. You can also do it the opposite way. You can have Snakemake manage individual Slurm jobs. And here you can find out more about how this works. And then you can say, for each rule, you can say, here I want to have minimum 4 cores, maximum 8 cores. Or for this other rule, I need 2 GB. And then it will manage the resources in a clever way. So you can do that too. And we talked a little bit earlier about Nextflow. Nextflow is a popular alternative to Snakemake, but there are many workflow management tools, and there is an overview wiki page that it lists, I think, all the workflow systems known to mankind. I think some of them have been accidentally invented during a PhD. So my recommendation is, if you want to try a different one, find the one that is popular in your academic discipline. So different disciplines have sometimes different preferences. And give it a try. I think it's really worth it. It's something I wish I knew 10 years ago. And now that we are almost out of time, I will try to catch up with some questions. Question 22, if I would make a change to the first step. Whether it would rerun everything. I think if I type just Snakemake and it has all the results available, it might actually not even have to rerun. Well, we should try it out though. I think we have time for that. So question 23 was, what if I make a modification to the first script? Will it actually rerun anything? Because I'm even not so sure about that. It was the number 46. Yes, it does rerun actually everything. Good call there.
Which makes sense because you've said that they're dependent. So if
Yeah,
a
it makes
dependent
sense.
file
Yeah.
changes, yeah.
Yeah. So, yeah, exactly. It does make sense. sometimes when you are instructing, then like my brain is here on the table, but
Yes, it's very difficult.
it does make sense.
Yeah.
So it will most of the time do the reasonable thing. You don't have to remember, did I rerun the right? If you change scripts or get new data, it will rerun all the steps that depend on it. And we are already 1 minute over time. I think I want to thank everybody for helping and for listening. I can stay a little bit longer and we can have a discussion, and I will try to comment on a few more questions.
Yeah,
Hopefully
thank
this
you.
was useful.
Yes, thank you, Radovan. Before we conclude, I would like to say thank you for leading the show. It was a great learning experience, and just kind of reminder to all the participants to give feedback for the day. One good thing about today, and one thing or many things you would like us to improve next time. Please give your feedback. This is very important for us to develop further courses and deliver it. And I would also like to thank Maiken and Enrico for helping out on the collaborative document, and all the questions, all the participants who ask questions on the collaborative documents. That makes this event very interactive. Thank you for your questions. And we will make this collaborative document publicly available after an edit today. And you will get an email from me when this recording are available together with the link to these documents. Yes. Thank
And
you.
please give us feedback. Tell us one thing that was really good, one thing that we should change.
I will stop recording, Radovan. Is that okay? And we stay here for a couple of minutes. Yeah, thanks.
Yeah.